GCE June 2019, question 1. Find the complementary function of the differential equation 2d square y dx squared minus dy dx minus 3y is equals to 5e to the negative x in the form y equals to f of x. Hence, find the particular integral and the general solution in the form y equals to fx. To get the complementary function of this differential equation, we need to bring out the homogeneous equation, which is 2d square y dx squared minus dy dx minus 3y equals to 0. So the homogeneous function is always the right hand side, which is this one, equated to 0. And then the next step is to get the auxiliary equation of this homogeneous function. To get the auxiliary equation of this homogeneous function, we need to set, let's say, a variable m to be equals to the derivative dy dx, and we set y equals to 1. It is just a method, and that's how it should always be done. That is, there are two derivatives here. So if I want to replace all the derivatives by m, I'm going to have 2m squared minus m minus 3 times 1, because we set y to be 1 is equals to 0. Now I need to solve this quadratic equation by the formula method. So to solve a quadratic equation by the formula method, let's say the quadratic equation is ax squared plus bx plus c is equals to 0. X is equals to negative b plus minus square root of b squared minus 4ac all over 2a. Now you see here, a is 2, b is minus 1, and then c is equals to minus 3. Then our variable here is m, so it means m is equals to negative b, that is negative into negative 1 plus minus square root of b squared, that's negative 1 all squared minus 4ac, that's 4 times 2 times minus 3 all over 2a, that's 2 times 2. Now we have m now will be equals to 1, that's negative times negative is 1 plus minus square root of minus square is plus 1 square is 1 minus 4 times 2 is 8. 8 times 3 is 24. Minus times minus is plus 24 all over 2 times 2, which is 4. Now m is equals to 1 plus minus square root of 25 all over 4. Square root of 25 is 5. So it means m is equals to 1 plus minus 5 all over 4. That means m is equals to 1 plus 5, which is 6 over 4, or m is equals to 1 minus 5 is minus 4, that is minus 4 over 4. 2 goes here 2 times, 2 goes here 3 times. I also know 4 here 1 time, 4 here 1 time. Now it means m is equals to 3 on 2, or m is equals to minus 1. Since minus 1 on 1 is minus 1, that is, the values of m are 3 on 2 and then minus 1. And the complementary function depends on the roots of the auxiliary equation. If the roots of the auxiliary equation are real and distinct, then the complementary function of any second order differential equation is given by the formula y equals to a e to the alpha x plus b e to the beta x, where alpha and beta are the roots of the auxiliary equation. That means in this case, the complementary function always denoted yc is equals to a e to the alpha. In this case, I will take my alpha to be minus 1 and my beta to be 3 on 2. It is always good to take alpha to be the smallest value and beta to be the other one. So it means e to the negative 1x plus b e to the 3 on 2x. That means yc is equals to a e to the negative x, since minus 1 times x is minus x, plus b e to the 3 on 2x is the complementary function we are also required to look for the particular integral. The particular integral of a second order differential equation denoted yp depends on the function on the right hand side of the differential equation, which in this case is this one. And the rule goes that if f of x is an exponential function, then the trial particular integral will be of the form lambda e to the alpha x. But in this case, our e to the alpha x here is e to the negative x. That is, yp is equals to lambda e to the negative x. But this yp also depends on the complementary function. That means if a term in the complementary function already have this exponential part attached to it, then we have to multiply the particular integral by x. That is, for this case, we already have a term in the complementary function with the coefficient e to the minus x. So it means we need to multiply yp by x. That is lambda x e to the minus x. So this one will be our suggested particular integral. To get the complete particular integral, we need to look for the value of lambda. To look for the value of lambda, I need to differentiate yp with respect to x one time and yp with respect to x two times, and then I substitute here and then here, and then I equate to the right hand side, compare the coefficients and obtain the value of lambda. That is the yp dx is equals to lambda x d e to the minus x dx plus e to the negative x d lambda x dx. This is from the product rule of differentiation. Is equals to negative lambda x e to the minus x, since the differential of e to the minus x is the same like minus e to the minus x. In order to differentiate the exponential function, we always differentiate the power, that's the exponent, which in this case is minus 1, times the exponential function, which is e to the minus x. Now times this component out of the differential, then we obtain this plus lambda e to the negative x. As the square yp dx squared is to differentiate again one more time this function. That is the differentiation of this plus the differentiation of this, d minus lambda x e to the minus x all over dx plus d lambda e to the minus x dx. That is d square y dx squared is equals to the negative of d lambda x e to the negative x dx plus the differentiation of lambda e to the negative x dx, which is the same like the negative of this, since our yp was lambda x e to the minus x. So lambda x e to the minus x minus lambda e to the minus x plus the differentiation of lambda e to the minus x. The differentiation of lambda e to the minus x is negative lambda e to the negative x. Since the differentiation of e to the minus x is same like minus e to the minus x, so times lambda, which is a constant. So if I rearrange this, I'll have lambda x e to the minus x minus 2 lambda e to the negative x. Since plus times minus is minus, so when I take minus lambda e to the minus x minus lambda e to the minus x, I'll have this. Now I need to substitute this part and then this part in the differential equation. That is, in the place of the square y dx squared, I'll substitute the square yp dx squared, which is this lambda x e to the negative x minus 2 lambda e to the negative x. Here is multiplied by 2 minus into minus lambda x e to the negative x plus lambda e to the minus x minus 3y is equals to 5e to the negative x. It means this one will be 2 into lambda x e to the x minus 2 lambda e to the minus x minus into minus lambda x e to the minus x plus lambda e to the negative x minus 3 into y, which is the same like yp, that's lambda x e to the negative x, which is equals to 5e to the negative x. Now if I expand this, I'm going to have 2 lambda x e to the x minus 4 lambda e to the negative x, since 2 times minus 2 is minus 4, minus here is plus lambda lambda x e to the minus x minus lambda e to the minus x minus 3 lambda x e to the minus x, which is equals to 5 e to the negative x. So I need to put the like terms together. Looking at the term with lambda x e to the minus x, it will be this, and this one. We have 2 lambda x e to the minus x here, 2, and then we have 1 lambda x e to the minus x, that's plus 1, minus 3 lambda x e to the minus x, which is minus 3, which is the same like 3 minus 3, which is 0, lambda x e to the minus x, which is equals to 0. So the terms lambda x e to the minus x becomes 0. Now let's look at the terms lambda e to the minus x is this term, which is the same like minus 4 minus 1. Minus 4 minus 1 will give me minus 5 lambda e to the minus x, which is equals to 5 e to the minus x. That's the right hand side. So now here I need to compare the coefficient of e to the minus x, and the coefficient here is negative 5 lambda is equals to 5. That means if I divide all through by minus 5, lambda will be equals to negative 1. That's 5 cancel here, 1 time I'm left with minus 1. So lambda is minus 1. You know, our particular integral was in the form yp is equals to lambda x e to the negative x. So now in the place of lambda I'll put minus 1. So yp now will be equals to negative 1x e to the minus x, which is the same like yp is negative x e to the negative x. And this is our particular integral. So we are also required to look for the general solution of this integral in the form y equals to f of x. The general solution y is always equals to the particular integral plus the complementary function. You know, the complementary function of the differential equation was equals to a e to the negative x plus b e to the 3 on 2x. So if I substitute this complementary function and this particular integral in this equation, I'll have y equals to negative x e to the minus x plus a e to the negative x plus b e to the 3 on 2x. This is the same like y equals to a e to the negative x plus b e to the 3 on 2x minus x e to the negative x, which is the general solution of the differential equation.